Hi folks, I want to talk about how to solve some of the problems that you will find on page 167 in your text. So now would be a good time just to pause this video, go find your book, open it to page 167 and follow along with me since I'm not going to take screenshots and post those since you all have books and can look it up yourselves. Ready? Pause the video and go find it. Excellent. I want you to look at problem number 1. And problem number 1 says, suppose you want to burn a piece of magnesium that has a mass of 7.27 grams, and I'm going to write that down if I can get my pen to work, 7.27 grams of magnesium. And it says what volume of oxygen gas would be needed at 23 degrees C and 1.02 atmospheres. So we are given the conditions of 23 degrees centigrade and 1.02 atmospheres. And the question is volume of oxygen gas. Well, if this stymies you as you take a look at this, I think the first thing you need to recognize is they're asking you to integrate both stoichiometry and your gas laws. They're asking you how much oxygen you would need to burn that magnesium. So there must be a chemical equation involved. And you'll find that true for all these problems. So we're going to start with looking at the equation. When something burns, it's usually in the presence of oxygen. And because this is asking for the amount of oxygen, you can tell that that is what is going on. But combustion is not just a hydrocarbon, which we have called CXHY, but it can be anything that is combined with oxygen. The oxidation process can be called burning. So we have magnesium that is burning with oxygen in a synthesis reaction that then creates magnesium oxide. And because we have a 2, I really want to change the color. I don't like the color of this. It's kind of hard because I can't change the color. I'm going to have to do this all in black. I'm sorry. Oxygen is a diatomic molecule. There's a 2 here. So in order to balance everything, we need to put a 2 here and a 2 here. So the first thing I did was create a balanced reaction. Now I can use regular stoichiometry starting with 7.27 grams of magnesium to determine the quantity of oxygen that I need to burn that completely. So I'm going to go from grams to moles by using the molar mass of magnesium. Per 1 mole. And then I'm going to multiply it by the mole to mole ratio. And this is magnesium here. If I write it down, it reminds me that the 2 moles magnesium goes in the bottom per 1 mole O2 here at the top. And the 2 is I got from the coefficient for magnesium. There's no coefficient for oxygen, so it's understood to be 1. This is all fairly familiar. And I get an answer of 0.1495. Come on. There we go. It's all duplicated. Moles O2. I didn't take it to grams because when I'm working in gas laws, remember that grams is not one of the factors that we use. If we look at PV equals nRT, there's no G. N is number of moles. So I'm stopping at moles because I'm assuming I'm going to be needing to go on to gas laws and use number of moles. So the question is, what volume of oxygen would be needed at 23 degrees and 1.02 atmospheres? So now I'm going to plug it in to PV equals nRT, solving for volume, which means that V, I'm manipulating the formula, V equals nRT over P, because I divided both sides by P. You know how to do that, correct? All right. So now I can plug in my numbers. I have 0. Let's see if I can write this down. 1495 moles, which is my N. I have 0.0821 liters times atmosphere over Kelvin times mole. Yes, I am writing all those units down. My temperature is 23 degrees C, which is, you know, that is converted is 296 K. And I'm going to put this all over. There we go. 1.02 atmospheres. And this corresponds to the formula that I originally wrote. And if I wanted to go through and cancel my units, mole in the numerator, mole in the denominator, mole in the Kelvin in the numerator, Kelvin in the denominator, and then this is atmosphere in a numerator, atmosphere in a denominator, leaving me with just one unit left, which is volume, which is what I want. And when I solve this problem, and be careful when you use your calculator, this one it won't cause you as many problems as others because there is only one number in the denominator, but you key in the numbers in the numerator divided by, and if there is more than one number in the denominator, you need to insert that open parentheses, then number times number, close parentheses, in order to get the right answer. I keep seeing that mistake, so I'm going to reiterate that point. When we solve this, we get 3.56 liters and a lovely line right here, which I don't know what that's all about. And that would be my answer. I would circle it. So to reiterate, what I did to solve this problem, and I'm not really sure how to make it go up. Let's see. Here we go. Is first, I had to write the formula. I had to determine what the formula was and write it down. And then I had to know what number do I want to extract from that formula using stoichiometry. And since I'm looking for volume of oxygen, and it is the gas I'm talking about, I know that the number I will need is going to be moles and not grams, because moles will fit into PV equals nRT. Then I manipulated PV equals nRT, that formula, to get volume standing alone. I plugged in all the numbers. Remember to use liters and atmospheres and Kelvin so that I'm using the appropriate R. And then I solved that. That's the map that I used to solve that problem using stoichiometry and gas laws.